Alright, hello everyone. Today I'm going to talk about Chapter 4.1. Now, Chapter 4.1, I got two goals for you guys. First off, I want you to understand the basics of population dynamics, which is a really fancy way of saying I want you to understand how populations work. The second thing is I want you guys to understand how biotic and abiotic factors can affect populations. So, the first concept I want to talk about is the first one the book talks about, which is the idea of population density. This idea is pretty easy to understand once I think you get a hold of it. This is basically saying the number of organisms in an area. So, for example, here, my example is with Riyadh. Riyadh has 5,254 people per kilometer squared. You might be wondering from the math side, what does that kilometer squared mean? That just basically means 1 square kilometer. So if you drew a square over Riyadh, you'd find around 5,254 people per square kilometer. I also put my hometown here in here just to give you guys another idea and show you that you can kind of see my hometown is a little bit smaller than Riyadh, which it definitely is. Okay, the next idea. This idea is really better illustrated by your book, but I didn't feel comfortable posting the whole page up here because of copyright issues, because I don't want this video to get flagged. So, dispersion basically says there are three different ways you tend to find organisms in their environment. The first one is called random. Random's easy to understand. That just means the animals go wherever they want. There's no real rule behind how they organize themselves. A lot of herbivores are this way. Deer can be this way, which is an animal from my hometown. The cats of Riyadh are an example, but I think some students in class pointed out this may not be as random as I think it is, because cats do tend to be a little bit territorial, so they might be more in the uniform category. Second one is called uniform. Uniform are basically organisms that are evenly spaced. These organisms typically like to protect their territory. They usually have their spot and they say, this is my spot and no one else gets here. That's what a uniform organism does. A bear is a good example of this because they protect their territory and they don't usually go outside of that unless they're going to fight for more territory, which then pushes one group out or one group to get more space, basically. The last one is called clumped. These are just organisms that appear together. Any kind of herd organism is this way, and organisms that arrange themselves in families. So some good examples I heard in class were things like camels, monkeys, ants, humans are all good examples of clumped organisms. Now, there's two ideas here this book talks about, and this can be very difficult to understand in a good way. It's easy to think of examples for this because one's basically food, water, things like that. The other one's basically natural disasters. But really understanding this can be kind of tricky. The first one is called density-dependent limiting factors. What this basically says is that these are limiting factors that depend upon how big your population is. So as I have here, I say the more organisms there are, the less stuff there is to go around. And the example I always give in class is that if I have 1,000 organisms in an area and I only have enough food for 800 organisms, well, that's going to create a density dependent limiting factor. That means that the number of organisms is going to go down because you can't have more animals than you have food to support those animals, and that's going to limit how big their population is going to be. So it'll put them down to 800 from the 1,000 they were at before. So that's where you get the limit part of this idea. The second one is called density independent factors. Density independent factors don't care about how big your population size is. These are usually natural disasters, weather events, things like that. So if a rainstorm is going to wipe out half of your population, then it's going to wipe out half of 50 will be 25, half of 1,000 will be 500. It's still going to wipe out a large number of your population, and it will limit how big your population can get. The classic example of this one, I wish I could find the name of the bird species because it would make it a lot easier to understand. But there's a bird species in the United States that every about 10 or 20 years, there's a massive windstorm in the central United States that tends to kill about 70 to 80% of this type of bird. And what that does is that lowers their population. So every 10 to 20 years, this population of birds has their population basically cut by 80%. That's going to prevent them from growing to a decent size in population. So that's a density independent factor. Any kind of natural disaster can act as a density independent factor that would limit how big your population can get. Okay, here's an example of our own species. This is your way of kind of seeing what I'm talking about. So, density dependent factors. The question here is, do we have enough food for every single human being? If we don't, well, there's starvation. That's pretty kind of easy to see that. If you've ever read any of your history classes, you know that starvation happens around the world. Starvation is a result of density dependent factors and some economics. The second part is what we call density independent, which I think I just used the wrong term for the last one. It was density dependent. Density independent factors are things like floods, tsunamis, fires, volcano eruptions. These all tend to kill human beings and lower the population. Now, most of you guys, I know one of the students in class mentioned, well, what about the Japanese tsunami? Would that be a good example? Or the Philippine tsunami? Unfortunately, yes. Both those would be density independent factors. They did lower the population. The last one is clumped. Clumped is a dispersion pattern because we typically live, in large families and large communities like the city of Riyadh. We aren't randomly distributed. He goes, I don't typically care too much about territory. Now, some students in class pointed out that we kind of have a uniform pattern as well because we do care about territory. And that's an interesting point. And he goes, I would give it that on a quiz. As that I can see that argument does make sense. Humans do care about territory. And if you look at hunter-gatherers, we definitely fit the clumped pattern and the he goes, we definitely, and the other pattern as well. I'm drawing a blank all of a sudden. Sorry, guys. I'm sure you guys know what I'm talking about now. So we definitely fit both of those patterns. So I would give you guys that. Okay, this idea is population growth rate. This is basically how fast a population grows every single year. So, for example, Saudi Arabia is currently growing at about 1.5% per year. So today you have 29 million people. In 10 years, you'll have around 35 million people. And how you can calculate that is you take 29 million multiplied by 1.015, and you get 29.43. What that basically means is you're adding over 400,000 people to your population every single year. That's really all that idea says. Okay, populations tend to move in two ways. There's immigration and immigration. Immigration is basically organisms leaving the area, and immigration is basically organisms coming into the area. A good example of immigration would be the Egyptians who have been leaving the country. I think there was like 300,000 left Saudi Arabia in the last few months due to the crackdown on ikamas. And those would be a good example of emigration. They are humans leaving the region. Immigration is the opposite. That's what Mr. Russell is. I'm an immigrant. I've come to this country to work. So I have increased Saudi Arabia's population. Okay. There's a big question we have in population dynamics. That's the idea of how many organisms can you have? And that's the idea of carrying capacity. That's just saying how many animals can you have here? One of the key ideas here is obviously a limiting factor. He goes, your limiting factors are going to tell you what your carrying capacity is. And then I give you some examples of what can limit the number of organisms. And you have food, water, disease, predators, all those kind of things. Now, I was watching BBC Earth's documentary, and they made a very cool point about rainforest limiting factors and carrying capacity. And one thing they were saying is that diseases act as a density-dependent limiting factor in the rainforest because when a population gets too big, typically fungal infections from the fungus cordyceps tends to kill off large numbers of those animals, bringing their population back down. And then another population will move itself up. The cordyceps fungus will knock them back down, and it every single time a population increases, the disease acts as a density-dependent limiting factor that brings the population back down. Okay, now there are two growth models we talk about in population dynamics, and both of these are a little bit deceptive because they're not the full story. The first one we call is the exponential growth model. This is like the Russell challenge I gave you guys in class, where you start off with a very small number and it slowly increases for a few turns and then rapidly increases over time. Every population in the world grows like this. It's kind of one of those scary ideas because it shows that if you have one or two ants in the beginning, it doesn't take very long for those one or two to turn into several thousand, or other pests, or even human beings. We tend to grow this way as well. If you ever go into economics, you'll get a much stronger idea of how this idea works, because economics runs off of the exact same principles and the exact same mathematical equations, which makes it kind of interesting. Next one is the logistical growth model. This is basically just the exponential growth model, but it takes into account carrying capacity. This is growth with limits. So then the population grows for a while, reaches its carrying capacity, and then stops growing. Both of these graphs are somewhat deceptive because it's not really how it works. There's probably more of a combination model where populations tend to increase to a point, they go beyond their carrying capacity, and then they drop. But they typically will go back and forth along their carrying capacity, population size wise, but they never stabilize, not like this graph right here shows. Okay, that's the end of chapter 4.1, guys. Thanks you for tuning in. If you have any questions, feel free to post them onto Edmodo or to come talk to me during break time in class. And I hope you guys have an excellent day.